Hi, good afternoon, everyone. How's it going? Okay, good. There is some energy in the room because I was a little worried. I got that after lunch slot. Everyone's had dessert, and you're trying to process the sugar. My goal here is to go. So you heard from Aaron Benton. If you've been in this track the whole time, you've heard from Aaron Benton first thing in the morning about what Couchbase is and what the different components are. Then you heard from Munib about how you do a little bit of programming to Couchbase and how the architecture actually works out. And what I'm going to do is I'm going to go a little bit further than that. In fact, at the end, I'm going to go a lot further and try to confuse you. Well, not really try to confuse you, but at least try to expand your mind in terms of what you can do with Couchbase. And so I'm going to talk a little bit about leveraging the full power of the data platform. First, let me kind of give a little a bit of a metaphor. Just kind of show of hands. Who's a developer out there? Okay. Oh, fair number. Cool. So my background, software development. I run a software development team here at Couchbase. I'm part of the engineering organization. And you might be familiar with this metaphor. The metaphor is the API surface area, right? And so a lot of what we do with building that layer for developers to work with Couchbase is we really try to make it easy to work with, but very powerful. And believe it or not, there's a lot of artwork to that, if you will. It's not exactly a science. There is no class in comp sci on how to build a great API. You know, it's a little bit of iteration and understanding your end user and what works well. And so I kind of took this metaphor. I'm from Southern California, so we got beaches, and so I was starting with this sort of beach ball metaphor. And just to go a little further, oh, by the way, you can check it out later. That's actually not really a beach ball. So at the core, and you've seen that wheel diagram a number of times, you really have data, right? You're not going to be able to do anything else in the system without the data itself. And then we have a number of different services and ways that you might use those services in building your application. So I have a little bit of a joking kind of name for all of the services that I'll get to as we go along. So first, though, let's kind of characterize the services in terms of performance. Sometimes we don't actually talk a whole lot about performance. We like to talk about capabilities, and I mean in the industry at Couchbase we talk a lot about performance. But it may make sense to sort of think about what is, for lack of a better term, what's the operational complexity of a given service, and how does that translate back into the performance of the service? So just starting at one of the main services, which is the KV service. You don't have to start with the KV service. You can certainly work with some of the other services like Nickel. You can insert data that way. There are other ways that you might use the system. But the vast majority of applications can actually make really good use of that KV service. So just to give you the sense of what that system is capable of, the data service really is doing a direct fetch. In your application, when you request a given document, you're giving it a string, a name for that document. And the system, the SDK is actually going to take that name for the document, run it through a CRC32, so just a really quick computation, generate a hash, and then based on that, it knows exactly which node to go to in the cluster. And there are a couple of other systems out there like that, but it's relatively unique, and it's part of how we keep the really low latencies for being able to fetch items. In most other systems, even other systems I'd worked on in the past, I did some work with HBase quite a while ago, and I've worked with MySQL and some others. You're almost always going through a secondary index access before you know which node of the cluster to go to. But in Couchbase, as kind of depicted in this diagram there, you have a really simple application. This is a 3-node cluster. Obviously a sort of a cartoony diagram of a 3-node cluster, but I have that Java app, and it knows exactly which node to go to fetch an item. And that's what really gives us the ability to serve up data in about 20 to 500 microseconds or so. Gigabit Ethernet fits inside a packet is about 220 microseconds. 10 gig E, we've seen latencies as low as 12 microseconds. And just to give you a sense of it, a syscall on the system is 7 microseconds. And so we can serve up traffic at that rate. What happens when that client makes that request is it puts together a 24-byte packet header plus the name of the key, throws it across the wire, and the server just dereferences that to the appropriate place in memory, sends the response back. So from an operational complexity perspective, obviously very simple, and that's how you, by cutting out layers, that's how you can actually get high performance out of the system. So wanted to just kind of mention that. And then we'll build this up. So another, one of the other services, after you are, it turns out that basic key value access is not enough for many applications. Usually you have to find something, you'll need to find a user or range of users by maybe email address or something along those lines. And so you need something that can look into a secondary index, possibly do some projection, possibly do some transformation, maybe even do some other string manipulation there. And that is really where Nickel, the query service, shines. Now, Nickel's operational complexity is a little higher, of course. I sometimes like to say the great thing about Nickel is how expressive it is. The challenge with Nickel is how expressive it is, right? You can certainly you can build up a query that may not match a given index or may not be a covered index. That is going to take a lot longer for the system to execute, or you can express a query that might be exactly what you need. The beauty of it is that the query itself doesn't change, but you might have to work with the system in particular ways. So what I'm depicting in this part of the diagram is there's this arrow coming over from that application to a node, and then typically inside a Nickel query, you're going to go to an index. If there's no other specific index, it would be the primary index. And you're going to do an index scan, find the items that are appropriate, return those back to the query node. That index may be local to that node, it may not. That index may be sharded, or it may be on a single node. Come back to that node, process whatever needs to happen from a projection perspective. Sometimes, as you can see here, there are these little arrows in between. Sometimes Nickel will then have to fetch, the query service will then have to fetch the individual data items if the index doesn't have the data necessarily there. So the query service, this is an equal opportunity complaint set of slides in that I'm sure all of the teams can say, no, I'd never be seconds, but realistically, it could be seconds or even many tens of seconds if you're talking about a non-covered, basically scanning all the items. But when everything's set up very well and you're doing very simple things, it can definitely be well under a millisecond for a kind of query service. So just kind of characterizing a little further, building up the next level would be the full text search service. So full text search, if you were to characterize it, is an index scan, one or more index scans actually, because full text search always shards out its indexes across the cluster. And then after you do that index scan on those individual systems, you merge those results. Now, unlike a Nickel query, in full text search, for the most part, there are little things that we do with term highlighting and generating facets. But for the most part, there's not a lot of processing other than finding the items that apply. A lot of full text search, you put a lot of the upfront work into how you build that index, how you build the weighting inside that index, how you distribute that index, what analyzers are you using. But characterizing that, you're really talking about things that are sub-milliseconds to single-digit seconds kinds of requests. All of this, of course, varies based on amount of workload, but that just gives you a characterization of what you can kind of expect from the full text search service from a performance perspective. Then eventing. So much like query, eventing is very expressive. In fact, eventing goes much further, right? In eventing, you're given a function and you can write your own code, which is licensed to do lots of amazing work or lots of work that's slow. So that's entirely up to you. So with the eventing service, the operational complexity, that's a question of what kind of code you write. It's not really a question of eventing itself. Eventing is very highly scalable, parallelizable across the cluster. You can add more eventing nodes. So these diamonds represent nodes that are running those on-update functions, as an example, in response to documents changing inside the system. So it can probably be well below hundreds of milliseconds, but I think generally speaking, because it's flowing through an operational system where you have a lot of data flowing, you're really talking about how long will it take before you get an on-update function call and then have the opportunity to write back to a bucket, which is kind of what's represented here. The idea that I have, this application is writing to a node, then that is streaming over DCP to a function node, and then that function might be writing back to another bucket. Those are the arrows that I'm kind of representing here, and that probably is in the hundreds of milliseconds. Yeah, question?
Is it allowed in an event handler, on insert, on update, to do a query, a nested query somewhere else before you do your operation?
It is. Well, not so much before you do your operation. So you get called, and then sure, you can do a nickel query straight from there. Yeah. So and so you can imagine. In fact, you can do 2 nickel queries, or 3, or 5. So you can imagine the kind of complexity. Now, the really good news is it's not in the critical path, right? It's happening after the data update occurs. Sometimes functions and eventing is compared to triggers, right? In triggers, in traditional relational databases, you actually have the ability to reject a request, and it's happening in that flow. And intentionally, we've put this asynchronous, so you don't have the ability to do that kind of rejection, but it's not in the critical path. Doesn't really change the way the app behaves, but I just wanted to kind of characterize it. So that's roughly what eventing would look like. The cool thing, like I said, is that it scales just by adding more nodes to the cluster. So it scales linearly, effectively, by just adding more nodes. So if you write complex logic in your function, then you get to put more resources into the system, right? Next one would be analytics. So analytics is kind of interesting because from a functional perspective, you're using the same query language. Nickel and analytics are both converging on kind of a subset or superset, depends on where the engineering teams end up with it, of something called SQL++. So realistically, it's about the same thing, but the way it executes is very different. In the case of eventing, really what you're doing is you're scanning all of the data in parallel. And so a lot of the, did I say eventing? In the case of analytics, you're scanning the data in parallel. And so a lot of the analytics service is a system that really knows how to break that job down to execute in parallel across the system. So the kinds of things that we're targeting that for are those kinds of analytical queries. So think of things that are, if you're familiar with database terminology, low selectivity. I want to go. What's a good example? I want to go count up, maybe an IoT use case or something like that. In the last hour, there have been 1 million sensor readings that have come in. I want to go sum up those 1 million sensor readings. So I have to visit every one of those data items, and index won't necessarily help me for that. There's memoization and some other things that you might do. But that's the kind of use case, that sort of ad hoc, parallelizable job, and pushing it down to that lower layer. So if you're to performance characterize analytics, it's kind of in that 1 to 10 second sort of range, right? That's for most kinds of jobs. And then finally, there are views, which we've had since Couchbase Server 2.0. Perry remembers when we did that. So in Couchbase Server 2.0, in views are also an index scan. And then a resulting merge. And so what you're seeing in that diagram there on the right-hand side is the application's making a request of a node, and then that node has to go do an index scan on every other node inside the cluster, merge that result, and send it back. So a slightly higher operational complexity. You might say, well, why would I even bother? What's the advantage to that? Well, there are a couple. One is that it works with very high ingest rates because you have indexes across every node. And you can do that also with the global secondary indexes that we have for Nickel. There are some other functional differences with that, but it also generally, less than 1 millisecond might be, is probably a bit optimistic in certain cases because it's a fair amount of work to actually go out and do all of that. But I wanted to just kind of give you a performance characterization because you're in this 101 track and you're going to leave here and hopefully go write some awesome apps. And you're going to have to decide, okay, how do I approach this particular one? And particularly when you get to query and analytics, they even have approximately the same interface. And so understanding the operational complexity and performance characteristics might help you. Any questions on that? Is that useful? Is anyone asleep? In my last session, someone actually did snore. Yeah, nobody's snoring here. It was kind of funny. It was towards the end.
Maybe stupid question. Analytics, it's only related to query data. What is analytics?
Yeah.
Can you explain that?
Sure. So the question is, just to repeat it for everyone, is analytics only related to querying data? So in Couchbase, yes. Analytics could be, it's sort of like NoSQL. It could have a lot of different meanings. Yeah. So in our case, analytics is really taking a SQL++ statement. There are some minor differences. You'll see it in the documentation. For the most part, you don't notice, but there's some minor differences between Nickel and analytics at the moment. We're working to converge those. But it's basically a query string that is like a SQL statement, breaks that down into an AST, works out an abstract syntax tree, right? Then works that into typically a DAG, a directed acyclic graph, figure out how to process that across the cluster in parallel, and then pull the results back together and send it back. But from a user perspective, really all that's happening is you're doing a select, but it's designed specifically for ad hoc. So think of things where I'm not building an index for it. I'm expecting to have to scan all the data. Does that help?
The order is like as you mentioned. I mean, order of, was there any independent?
No.
Is there any order
Is
of?
there any order of performance characteristics?
No, hierarchy of the services.
Oh, is there any hierarchy to the services? Not really. I mean, the only one that there might be is data because you kind of need data to do the rest.
Then they all work in parallel.
Exactly. And then through MDS or multidimensional scaling, you actually have the ability to kind of decide what that topology looks like. Excellent question, because to that point, sometimes you may actually scale the query service up higher if the complexity of the query is relatively high, so it has a fair amount of CPU and memory requirements. And then there are lots of situations where maybe it's very simple queries, and so you don't need to scale the query service up as high. So that's one of the capabilities that we have. Yeah, question?
Is Couchbase looking at adding another service or an inferencing engine like machine learning so you can detect trends without having to write SQL++?
Yeah, so the question is Couchbase looking to add another service for things like machine learning to do inferencing of trends? And answer is there's nothing I think we're talking about public roadmap-wise at this stage. For sure, if you were to walk around the halls of engineering, you would hear people talking about that. Now, what we do is we do have a Spark connector that works with Spark ML, Spark machine learning. And we implemented in Spark has what's called Spark SQL, but there's an interface layer that allows us to push a lot of the execution of that down to either the analytics or to the query service. So you kind of get the best of both worlds, if you will. So you'll be able to pull the data. And we're actually, if that's an interest area, we're looking at where we want to go next with some of the machine learning. Historically, we definitely had people doing that with Hadoop. They would pull all of the data out into Hadoop, build a model, and then put the summary data back into Couchbase for online servicing. So Moving forward, so let me kind of characterize the services a different way, and so this being the 101 track, where now you're 4 sessions into understanding how the system works. I want to talk a little bit about use cases, and this is where I get to use some of my fun little language. So, use cases. The data service. What do you do with the data service? You find things. In this case, you directly find things. I have a document. That document's name is matt@couchbase.com. That's my email. So I want to retrieve that document. So I just hash it, go get that document from that particular node, directly get that document. There's not a lot of fancy work there. It's retrieve the document. But that works really well for a bunch of use cases. Things like user profiles. That's a really common one where with systems of engagement databases, people are building very large-scale sites. They need to be able to retrieve that profile and update that profile very quickly. As you know, right, some user has their mobile phone. If it's taking a while for the login to occur, oh, look, there's a notification about an Instagram from my friend, and now I'm lost user, right? So we need to be able to do that kind of thing very fast, very high throughput. Ad targeting. Ad targeting is another use case that we've seen over time. If I'm honest, we kind of stumbled into it. We just had these really low latencies, really high throughputs. And in ad targeting, when they're making decisions about which ad do I serve in a particular case, or recommendation targeting would be another example of that. They need that really low latency access to a profile to be able to make a determination. Do I show the dog food or the cat food ad? I need to find out really quickly. Another one would be application session management. Sometimes when you're building a large, engaging website, you might have certain sections. PayPal would be an example of this on Couchbase, where a user is walking through a workflow, and that workflow has to have a session that's associated with that workflow. And that workflow, that session information, you need to store it somewhere as you go to complete that workflow. Much like Peter was talking about earlier, at the end of it, there's a transaction, right? At the end of it, there's a monetary transaction, but there might be a set of steps in the middle of that transaction in determining where do you want the, what's in your profile, how do you want to fund this transaction, et cetera. Personalization would be another one, personalizing a site, and even, it sounds like a relatively boring case, but it still is extremely common, very high availability caching. Situations where you want to make sure that you're building a cache, but also if you have a failure inside the cluster, you don't have a cold cache situation or a hole in your cache that you're going to have to go back to a different primary system. Use cases in the query sort of world. So if KV or data access is finding things, this is finding things directly. This is finding things, with no directly. So you can just express what is the data I want to get from the system. So it's very expressive. What might you use this for? The persistence layer for your services or microservices. Any given application, at least an interesting one, is going to have some data associated with it, and so you might need to store that. So a number of our users these days are deploying lots of new microservices, and they'll deploy, say, a Couchbase bucket to back a given microservice.
Before you go on, I'm a little lost. What exactly does expressive data mean?
Sure. So the question is, what do I mean when I say expressive data access? In the case, I'll kind of give an example. There's in Nickel, you might do a select star. That is not very expressive at all. It's give me everything. Select star from user profile. Give me everything. But I might say select star from user profile where username is matt@couchbase.com. So now I'm saying one thing. I might actually want a projection on that. I want to be able to express maybe from the user profile for matt@couchbase.com, I just want to get the birth date or a couple of other components. So now I have select birth date, comma, a few other things. So I'm kind of building up this query that allows me to express very specifically what the data I want is based on the predicate that is in the latter part of the query. Does that help? Okay, cool. So things that, services and microservices, real-time chat, or in certainly a product or service catalog. And as you can see over here on the right-hand side, it's not too small. That's select name address from travel sample where name like crown. So here we are in the Crown Plaza. Full text search, finding things with ambiguity. Sorry, you said wrap up? No, you said wrap up. I was confused. Okay, I was confused for 1 second. So finding things with ambiguity. So this is full text search, right? So in the case of, this is kind of like a search engine. Anyone ever use a search engine? Okay, yeah. You don't do a select star from whatever. In the case of a full text search, really what you're doing is natural language searching. So it's language aware. It's doing things like scored results. This also works for product or service catalog. Geolocation search is one of the other capabilities there. Eventing. Oh, I'm skipping over my my cheeky little descriptions. This is finding things with ambiguity. So I'm not being extremely specific about what I'm looking for, but I'm just finding with some ambiguity. So the search in that particular case, unfortunately the slide's a little small, is Times Square. And of course, it came up with Times Square somewhere in the UK. So that was too ambiguous. So you would have to kind of train the system or put some weightings into it in the case of full text search. Eventing.
What about full text search? Is there any relationships with the clustering?
Yeah, the question is there any relationship with full text search and clustering? So the way we see it at Couchbase is really we're giving you an API that is pretty independent of the cluster. So all of the services scale across the cluster. You don't have to know the details. Now, in fairness, sometimes with abstraction layers, certain details sort of leak through, but you don't generally have to know about the details of how it works in the cluster, so it's definitely clustered.
Depend on what clusters are.
No, the result's going to be independent, yeah. And as you add nodes and rebalance, you will continue to get the same results. And the results might change based on how you define the index and the weighting. Just to try to make it through everything else, I'll hold any questions till the end, but I'm certainly happy. Oh, no worries. I'm certainly happy to stick around at the end. So use case analytics, this is finding insights on your things, like the IoT example I gave earlier. If I want to add up or calculate the average over a bunch of sensor devices that were sent in. So think of business KPIs, key performance indicators. Fraud detection. To the question earlier, model training. I might have a machine learning model and I need to feed it with a certain amount of data, and so analytics can allow me to express finding that kind of information. Views. Views are kind of interesting because it's map reduced, so you're able to do transformation on the data before you index it. So that's find things where you put them. Optimize aggregations over the data, and so forth. So I want to get through a couple other things. So I'm going to move a little faster here. I guess I was going on a little too long earlier. So concurrency, so wanted to give you a sense of, okay, so it's this distributed system, but for a distributed system, we do need to think about how do we handle concurrency, right? What level do we expose to the user? In that particular case. So I want to give you just a sense of some of the more advanced kind of capabilities. So there's certain concurrency primitives, consistency considerations, and durability requirements, and then we'll kind of wrap that into transactional semantics. So when you first start using Couchbase, you will probably not use any of these things, but there will come a day that you will say, I really want this behavior that I have a number. Say that number is currently 42, and I want two people to get the next number. It's a sequence, and they are going to race. So the behavior we want is one of them is going to get 43 and the other one's going to get 44. We don't really care who gets what. We just want to make sure that they each have a unique number. And so Couchbase has atomic integers built into the system. So you can define an atomic and then you can increment and decrement it as different actors are working inside the system. just a quick example of how you might do that. You define, in this case, it's a URI. Maybe you're counting up the number of times people go to that URI. So you might want to count the number of hits effectively. You'll define the counter, and then you'll increment that counter as people access it. This one gets a little more advanced. There's something called compare and swap. And so the idea of compare and swap is what we're doing is giving you an optimistic concurrency control. So you have a scenario, as you can see in the diagram here. I have a couple actors inside the system. They're both going to want to change a given document. And really the behavior we want is that we want one to be successful and the other one to be unsuccessful, because we don't want the second one to possibly overwrite the first one's change. And so we don't want to serialize that access if it's the kind of thing that is infrequently changing or something that is very easy to change in a different way. So let me give you an example. Maybe I have a document that has reviews for a given product. If I want to add another review to that product, I'm really extending an array. I'm changing an array at the end of the document. How often do things get reviewed? Probably not very often. So most of the time, I'm going to retrieve the document, modify it, and set it. But every once in a while, I might have a collision. And then for the one that collides, so as you see in the diagram, one actor is going to be successful, the other one is going to fail. In that failure case, you can actually just have that in a do while loop, because really all it's doing is trying to append on to the end of an array. So it takes one more round trip on the system, but versus traditional non-distributed databases, we get a huge performance advantage out of not trying to slow down the world and serialize the world for data access to something. Moving forward, so talking a little bit about consistency, we have very flexible consistency inside Couchbase. So when you query, directly through the data service fetch an item, it's always consistent. And we think that that's really the right model for most interactive applications. When you start talking about secondary indexes, so just to give you an example, maybe something like a leaderboard. In that case, does it really matter what the score is between two people on the leaderboard at a given point in time? If you were to check a second later, it will probably be different. So you're kind of sampling in a way. So in that case, a so-called eventually consistent secondary index might be entirely appropriate. So you're basically trading off the amount of time it takes to get, you're getting lower time by having less bounds on consistency. But we have that as an option. So there might be another case where I'm doing a query, finding a record, modifying a record, and then I go back to the query, the so-called data table with a record detail, and then going back to the data table, which is a very common pattern. You may have that scenario, and really you don't want to have that scenario where I change a record and then I go back to the query and suddenly it's not changed again, and I went, what's wrong with this thing? So you want to be able to define, in that case, I might want my secondary index to be consistent with respect to any changes I've made, so-called read your own rights consistency. So that would be not bounded, request plus, or starting in 4.5 and later, we have a more advanced version of that called app plus. And then finally, durability. Durability really allows you as an application developer to express to the system what you expect as far as having a record change be durable. It used to be durable was sitting on a disk somewhere, right? But the challenge there is that in a modern distributed system, if a given system fails, I'm not going to wait until I get that system back online to be able to keep the application going. Technically, there's sort of a tension, if you will, between availability and durability. So what we give you at the application level is the ability to express to the system, I consider it durable, say, when it's in memory in 2 locations, or when it's in disk in 2 locations. And we actually think that's a pretty good trade-off, because the application developer has context over how durable they need something to be. You can turn, these are 2 independent things, so you can actually turn them both up as much as your cluster allows. So you're basically setting your paranoia level, and that'll make your application block until we meet that durability requirement. So on a cluster, you might consider this change, it's durable enough if it's in memory in 2 locations. You know, is that truly durable? I don't know. You know, it's like what is the durability of an ephemeral disk on Amazon EC2, right? It's an interesting philosophical question. And then finally, I'm going to wrap up with one other area, because this frequently comes up, is if you think of the last few things I said, you could actually kind of look at that in sort of transactional semantics, you know, kind of comparing it to something that you already know, so-called ACID, right? And realistically, and I can go on, there are a couple of great papers. There's one called Acid Rain. There's another set of, that's a good technical paper. And then there's another set of papers by a researcher named Martin Kleppmann. Even in the world of ACID, it's not necessarily clear what all those things are. But a lot of what I talked about could be cast in those terms. So what does Couchbase have? Couchbase really has atomicity at the document level. And at first you might say, well, it's just to the document level. That's not very useful. But consider that in Couchbase, you are able to denormalize the data. So you're able to put an entire user's record, or if you were to look at classic examples of like order entry kinds of systems where I have an address and a set of line items, I'm just putting it all into a single document. So treating that atomically is actually pretty useful, where in a traditional relational database, I sort of need a stronger atomicity guarantee because I have to normalize the data across lots of different structures inside the system. Consistency. In the world of ACID, that actually means a couple of different things. It might mean enforcing a schema, or it might mean query and index consistency. We already have, as I said, multiple levels for you to express as an application developer of query and index consistency. And then as far as enforcing a schema is concerned, we've decided effectively that we're flexible schema. We're deferring that to you, which we think is a really good trade-off here in the modern world, because how many people really like database migrations? Anyone? Anyone? No? Really?
It gives you job security.
Job security, okay. Database migrations for job security. And then finally, a couple of other things, transactional semantics. So isolation. Isolation could be considered really, if you, in the relational database world, that really comes all the way down to serializability, where you might say, I want to make sure that for any set of changes occurring through the system, I have a guaranteed order for them, right? If you want to take a distributed system and make sure that you have a guaranteed order for how everything happens in a distributed system, you're basically making it a non-distributed system. So you're going to lose all the advantages that you have of being a distributed system. However, we have isolation with the CAS, optimistic concurrency control, as I'd mentioned. And there's also a further capability for pessimistic concurrency, the so-called get and log command. And then, of course, the D in ACID is durability, and I've already sort of addressed that. You know, durability, as Ravi even said this morning, as a database, durability is required, but really there's sort of a question of, like, what is durability here in the modern world? As Wayne had probably talked about in the last presentation, is it durable when it's on the phone, or is it only durable when it's on the phone and synced? In a cluster, is it durable when it's in 2 nodes, or is it durable when it's in 2 nodes and on disk? So with that, I think I am pretty much out of time. So I want to just say, any questions? One in the back.
So I hear that in Couchbase there is no single point of failure like.
Yep, no single point of failure. Yeah.
Yep. So the way I understand is when you mentioned in your initial slides, the search is pretty quick, like some microseconds.
Mm-hmm.
So for that, you have various buckets and then documents inside those buckets. So for full search text,
Full text search?
Yeah. FTE, or for that per se, when you are doing queries, which as such has to, and when you build secondary indexes, how does this happen? The way that I see is like, do you really store the metadata at a document level, in memory to do this, to build this faster search?
Yeah, so that's a fairly complex question, but here's the quick answer. The quick answer is, in the case of FTS, and this is true in the case of GSI or MOI indexes as well, or I should say plasma. We have different versions of our other secondary indexes. You can define the index such that it either includes the data or so that it doesn't. You kind of have some flexibility there. So while it's true that there's no single point of failure, the one trade-off there is that there can be certain classes of failures that for a brief period of time, until auto failover kicks in, the rest of the data might not be available. So that particular request might fail. And this happens all the time on scalable systems. You know, at Google and so forth, there are failures all the time. And so that might impact the search results, but it doesn't impact your getting search results, as an example from Google. So great. With that, I want to say thank you very much. Please remember to write us a review. We'd appreciate it. And well, I think it's, 2 days left on the DBTA award. So thank you very much for taking the time, and I'll see you later.
Thank you, Matt.